Alright, so this video is about Newton's universal law of gravitation. And so we start with like what we already know about gravity. So we have this equation, Fg equals mg. And so the intro to this idea is that this equation only works if you are describing something that is on or near a planet's surface. We know that on Earth, in Earth's atmosphere, g equals 9.81 meters per second squared. And so we can calculate the weight of something by taking its mass and multiplying it by 9.81. And so now we're going to talk about like what that is and why you can't just use that anywhere. So this value of g, any value of little g, is known as the gravitational field strength. And that gravitational field strength has units of newtons per kilogram. And so this is something that is anywhere in the universe. So the gravitational field strength is something that can be used to describe every location in the universe. Inside objects, outside objects, far from objects, close to objects, etc. The way that we can show this, the units anyway, is if we take this example, this equation, and we say g equals fg over m. It's now pretty easy to see that newtons per kilogram are the units that make the most sense, because the force of gravity on something, it's a force, so it's in newtons, and then mass is in kilograms. So we have used g equals 9.81 meters per second squared. So now we have like two things that this variable does. So when something is accelerating through the air, we say that the acceleration is equal to negative g. And this is where negative 9.81 comes from. If an object is actually accelerating, we use 9.81 meters per second squared. But if we are just describing the effects of gravity in terms of forces, then we describe it as gravitational field strength. So meters per second squared and newtons per kilogram must be the same units, and they are. So every planet and moon and star has its own surface gravitational field strength. And so like this little person, if this is Earth, they're feeling a gravitational field strength of 9.81 newtons per kilogram. Now, on Earth it's 9.81, on the Moon it's like 1.6, on Mars it's 3.7, on Jupiter it's like 25. So each planet and object in the universe has its own gravitational field strength. And that happens because everything has a different mass as well as a different density. And so this lesson is about like how we expand that. So the truth of the matter is, if you take a person on Earth's surface, then they will experience g of 9.81. And if that person climbs a mountain, specifically Mount Everest because it's the highest, but really any mountain will do, as this person climbs the mountain, they will experience less and less gravity. On the top of the mountain, g is less than 9.81. Now, if we're talking about Mount Everest, then it's probably like 9.75, and a person is not going to notice that. They're going to notice how little air there is to breathe and how hard it is, but they're not going to notice that there's less gravity, but there is. And so the further a person gets from the planet they're on, the less gravity they feel. And so that's what we're going to explore. And so this law is called Newton's universal law of gravitation. And it describes the attractive force between two objects, and I'm going to call them big M and little m. Your equation sheet calls them m1 and m2, that are separated by a distance r. And so Newton's universal law of gravitation is an equation, and it's called the universal law because it works anywhere in the universe. And so this equation, again, right, this is like the terrestrial equation. If something is on a planet's surface, we can use this equation to describe the effects of gravity. But if we are not at a planet, if we're talking about the forces like between planets or something like that, we need this universal law. The equation looks like this: capital G, capital M, lowercase m, over r squared. And so that's the universal law of gravitation. And so the two masses, big M and little m, are there, kilograms. The distance that they're separated is r in meters. And then this value of big G is 6.67 times 10 to the negative 11th. It has units, we'll get to that in a second, but big G is a really, really small number. And so the point of that really, really small number is that it takes really, really large masses for the force of gravity to be noticeable. Now the units for big G are Newton meters squared per kilogram squared. You do not need to know about those units. You just need to be able to use them if you're doing a calculation, but you're not going to do that many calculations. So we have this equation, and it describes any force of gravity between any two objects anywhere in the universe. Now, if I graphed something, if I graphed the amount of force that objects feel based on how far away they are from one another, I would get the following curve. And this curve is the shape of what we call an inverse square law. So the proportionality is that the force is proportional to 1 over r squared. And so it's a really important proportionality because it actually describes the type of relationship between distance and a couple different forces. And so when we talk about gravity and electricity, they follow the same idea. So what this means is if you get two objects that are really close, their force between them of attraction becomes really large. But as you start to separate them, that force dwindles really quickly. But very importantly, that force never goes away. What that means is this force of gravity has an infinite range. There is nowhere you can go in the universe to escape gravity. It can be really small, but you can never make the force of gravity on you zero just by going far away from everything. It takes different techniques to make the force of gravity on you zero. Okay, so that covers the relationship. Let's just look at a visual. So we're going to pretend that this is Earth and this is the moon. The first thing is this universal law has to work everywhere in the universe. And so if the Earth is a big, massive object and you are standing on the Earth, how do we measure the distance between you? We measure the distance between you and the center of the Earth. That's the value of r for you. And if we pick an accurate value of r, plug in the Earth's mass and your mass and big G, we would get your exact weight. If we did this for the moon, we would have to measure the distance not between the surface of the Earth and the surface of the moon, but the distance between the centers of those two objects. And so really, when we say it's separated by a distance r, we say that r is the distance between the object's centers of mass. So this value of r, it's not just any distance. If you stick a meter stick on Earth's surface and measure it to your foot, that's 0 meters. The distance that you have to measure is between the centers of mass of the two objects. Now we'll talk more about center of mass, so I'm going to breeze through this. I want you to understand right now that because every object that we interact with is three-dimensional, it takes up a lot of space, that not all of the mass is concentrated in a single point. But we can understand a lot of physics if we imagine that the geometric center, right, the actual center of an object, is where all the mass is concentrated. So if I take my pen, my pen is not totally symmetrical, but the center of it is about here. the center of mass is about there, that means like that's the average location of all the mass. Now projectiles follow a parabolic trajectory. If I threw this pen, it would go like end over end through the air. But what would happen is the very center of it would trace a perfect parabola. So the center of mass is the location of an object that follows all of the physics that you've learned so far, and more. For us right now, we're going to pretend that the center of an object is also the center of mass. What you will quickly learn is that that's not true. But we're going to pretend it is now, because in space, for AP Physics 1, we deal with things in pretending that they're circles, and so the center of mass is the center of the object. So, if you're setting up an equation for this law, and it's between the Earth and the Moon, you would take the mass of the Earth, the mass of the Moon, and then the distance between the center of the Earth and the center of the Moon. So, you would have to okay, what's the radius of the Earth plus the distance from the surface of the Earth to the surface of the Moon plus the radius of the Moon. And there we go. So just a couple more things with gravity. There can be many forces of gravity. In fact, as you sit here watching this video, there are millions of forces of gravity on you now due to all of the people and things around you and Earth. It's just that it takes a really big mass to have a force that's noticeable, and so the only force of gravity that you actually feel is the one due to the Earth. So in space, all the celestial objects are pulling on one another. During a solar eclipse, the moon is positioned between the Earth and the sun. And that means that the moon feels a net force of gravity that's due to both the Earth and the sun. And I just wanted to explore that right now. So we'll put the moon in the center, and we'll say the net force on the moon equals the mass of the moon times its acceleration. Now, the moon here is in between the Earth and the sun. That's how a solar eclipse works. So I want to label some forces. The sun is going to pull to the right on the moon, according to this diagram, because gravity is only an attractive force, and so the sun can only pull the moon to the right. And then the Earth produces its own force of gravity on the moon. Remember that gravity is also everything subjected to Newton's third law. So the Earth and the moon pull on one another with equal forces. And then also the sun and the moon pull on one another with equal forces. But the sun is pulling with a different force than the Earth on the moon. So that's where the net force comes into play. So this is our free body diagram. So you can decide for yourself which direction is positive, but I'm going to decide that the direction that the sun is in is positive, which means that the net force on the moon is going to be the force caused by the sun minus the force caused by the Earth. And then that's going to be equal to the net force. So the mass on the moon times the acceleration. And so we're just noticing that there's multiple forces of gravity. And we also want to note that this means that it's possible or plausible, I guess, that the moon could feel a net force of 0 due to gravity from the Earth and the sun. And so one thing I might want to think about is how would that be possible? I'll write out the equations. So the force of gravity from the sun is going to look like this. Now, I'm going to use A and B as distances, and so that would be distance B squared. So that would be the force of gravity due to the sun. The force of gravity due to the Earth would look like this. And I'm going to use distance A. And that's going to equal mass times acceleration. And so, a couple things to notice about this. If these two forces are equal, then the net force is 0, and the moon would experience no acceleration. That would be kind of weird. The moon would just kind of like drift in a straight line for a little while until this net force was 0. The other thing to note is that according to this equation, since there's the mass of the moon appears in every term, it would cancel. And so the net force on the moon due to gravity from the Earth and the Sun doesn't actually depend on the mass of the moon. The moon will accelerate just based on the mass of the Sun, the Earth, and the distance. Now, we know that like the Earth is much closer to the moon than the Sun is. So this distance A is really small compared to distance B. And so this is a reason why like it could be plausible, although not realistic, to have the force on the moon be net force of 0. Because this value is small and the Earth's mass is small. That would mean like a similar ratio to a big mass of the sun and a big distance. So if these ratios ended up being the same, we would get a net force of 0. However, the Earth is so much closer that this is a much bigger ratio than the sun and its distance ratio. And so in this case, like the acceleration would be less than 0 all the time, because the Earth is so much closer, it produces a much bigger force of gravity than the sun does. Last topic here is that we actually know the value of little g on every planet in the solar system without ever having to visit it. And so we can like infer some things about what happens on a planet based on what we know about the way gravity behaves. So let's go back to this object on the Earth. We know that this object on the Earth would have a weight that's equal to mg. We also know that anywhere in the universe, the force of gravity on something is given by this equation. Now, when this object is on Earth, they have to be the same. These have to return the same value when on a planet. And so we can set them equal to one another. So we can say mg, which is our like equation for calculating gravity on a planet, has to be equal to g, big M, little m, over r squared. And that's our equation for calculating gravity anywhere. Mass is on the same on both sides again, right? Like this little m is the mass of the object on the planet, and so that's going to cancel again. And we have this equation that reads little g equals big G times big M times r squared. And this equation, if we have the data, can help us predict the value of little g on a planet, no matter where it is, if we just have two things. In this equation, m is the planet mass, because, you know, this equation can be for anything. It can be like a pencil and another pencil. But this equation is only useful if we're talking about like planets or moons. So this would be the planet's mass, and then r would be the planet radius. And so like kind of the crazy thing that Newton and other physicists did is they figured out the mass of a whole bunch of other planets based on Newton's universal law of gravitation. So radius is kind of easy. As long as you have a way of knowing what your telescope is seeing and how far away it is, you can literally measure it on the screen and get a reading of what the radius is, or at least an approximation, if you know how far away it is. The mass is a little trickier, but using Newton's universal law of gravitation, the mass of planets can be inferred based on how they pull other objects toward them. And so, you know, orbits of planets can wobble, and the wobble happens when other planets get near them and they experience more gravity than usual, or when planets are really far and they experience less gravity than usual. So they don't follow perfect paths, they wobble because of the effects of gravity from nearby planets. And so using that data, astronomers can calculate the mass of planets and then calculate the value of G on every planet. So having never visited Jupiter, we know that it's around 25 newtons per kilogram. And that's it for our lesson on gravity.